Good morning, good day, good evening, everyone. It's my pleasure to introduce today's speaker, Professor Sarbani Basu, who is professor at the Department of Astronomy at Yale University and now is current chair of the department. She received her PhD in 1993 for work done at Tata Institute for Fundamental Research, Mumbai, India. Consequently, she did her postdoctoral work in helioseismology. She was a postdoc at Queen Mary and Westfield College, London, and University Aarhus, Denmark, before moving to the US in 1997 to join the Institute of Advanced Study in Princeton. And then she joined Yale University in 2000. Sarbani's PhD thesis was on the topic of galactic chemical evolution, and she decided to shift her research focus to helioseismology because of superb quality of the data available in expectation of even better data from the Gantt network and helioseismology instruments on SOHO. She has been studying both the general properties of and the details of the structure and dynamics of the Sun, focusing on solar cycle dependencies. Her interest in putting the Sun in a general astronomical context has led her to use astroseismic data obtained by Kepler spacecraft to study other stars. Sarbani received the Vainu Bappu Gold Medal of the Astronomical Society of India in 1996 for her early work on helioseismology. She was elected as a fellow of the American Association for the Advancement of Science in 2015. She was awarded the 2018 George Ellery Hale Prize of the SPD, and she currently serves as the board of directors of Association of Universities for Research in Astronomy, the organization that runs the National Solar Observatory and other U.S. astronomical facilities. And today we will be listening talk entitled Studying the Internal Structure and Dynamics of the Sun. So please go ahead and I will give you warning 5 minutes before the answer. Please go ahead.
Thank you, Gregory, and thank you for giving me this chance for talking about my work, in particular, how we go about studying the internal structure and dynamics of the Sun. We have a lot of very, very good data to study what happens in the visible surface of the Sun. And as of about 30 years ago, we have data to study what happens inside the Sun. And we do so by means of seismology. So the field is called helioseismology. So, of course, like many words in astronomy, it's a Greek root, helios for the Sun, seismos for tremors. And what we basically do is look at pulsations of the Sun and use those to figure out what goes on inside the Sun, because the frequencies with which the Sun pulsates depends on the internal structure and dynamics. So we are lucky because it's actually, for most stars like the Sun, it's a very simple physics problem. The Sun and stars oscillate in normal modes, which are easy enough to calculate. And stellar oscillations in particular are standing waves, which makes the physics even simpler. So we basically, what we do is look for standing wave solutions. So let me go ahead a bit to show what really happens. So where do we get the oscillations from? So in the Sun, the outer 30% of the Sun is a convection zone, so a lot of movement of matter. And the top of the convection zone is characterized by very strong, very narrow downflows. And our current belief is it's those downflows that are exciting the oscillations of the Sun. And unlike classical pulsators, where only one or two modes are excited, only the few modes that are in resonance with the exciting mechanism, convection is a stochastic process, so we are basically looking at modes that are excited stochastically. So the amplitudes are low, but on the other hand, if you wait long enough, you will see many, many, many modes that are excited, since we're not just looking at modes that are in resonance. So let me give you a crash course in helioseismology. Let's get down to the more practical details. So a star like the Sun oscillates in millions of different modes. That doesn't mean that we can detect all of them. Now, in the case of the Sun, we can easily show that the oscillations are linear. We're talking about velocity amplitudes of 10 centimeters per second, when the sound speed, which is the scale we have to measure it against, is about 10 kilometers per second. So definitely linear. And we assume they're adiabatic. Now, this is a slightly more iffy assumption. In the interior of the Sun, this is a perfectly good assumption. At the very outer layers, it may not be very good because the heat transport time scales become of the order of, can become very similar to the frequencies, the periods of the modes. Now, in the case of the Sun, all the modes that we've observed are either P modes, which are P for pressure. These are basically sound waves, so acoustic modes, or surface modes, which are called F modes. There have been reports and there have been claims of looking at, detecting G modes, G for gravity. These are modes that are supported by buoyancy. I'm a bit skeptical, put it that way. So all the results that I'll show you today are from P modes, which are sound waves, and F modes, which are basically simple surface waves where the dispersion relation is simply omega squared equals gk. Now, to set a bit of nomenclature, we characterize each mode. It's a three-dimensional mode, so we need three numbers to characterize them. One is the radial order. This is the number of nodes in the radial direction. We can't see that, but we can estimate it from the power spectrum. L is the degree of the mode, and that's the number of nodal circles on the circumference. So L of 0 is the radial mode, that's the breathing in and out. L of 1 is the dipole mode, when half the sun goes in while the other half goes out. L of 2 is the quadrupole mode, and so on. And with Gong, current version of Gong, in principle, you can see modes up to LF more than 1,000. Similarly with MDI, with HMI, in principle, you should be able to go more than 3,000. Though technically speaking, we, at least for the sort of work I'll be talking about, rarely use modes which L greater than 200. And that's because the high L modes, they have very large line widths, so measuring their frequencies is a bit more troublesome. And then the third number we have to deal with is M. M goes from plus L to minus L, and it is the number of nodes on the equator. So basically, given that we are a spherical system, the modes are represented by spherical harmonics, YLM, with n being a separate function talking about the internal distribution of the mode. Now, if the sun were spherically symmetric, we would not be able to define an equator, which means all modes of the same L and N would have the same frequency no matter what the value of M is. Now, the sun may be spherical, but it rotates, so it's not spherically symmetric. And rotation lifts these degeneracy, because rotation means we can actually have a well-defined equator. And this basically, this rotation then splits a mode, an NL multiplet, into modes that are, so each M has now a different frequency. And you can show that the difference in frequency of a plus M and a minus M mode can easily be related to the internal rotation. Well, it does involve a few pages of mathematics, but it's not particularly difficult mathematics. Now, I mentioned that in the sun, we often use L's of about 200, which means M's can go from minus 200 to plus 200, so 401 values of M. That becomes difficult to fit and noisy. So instead of finding the frequency of every individual peak, you instead define the frequency of a mode characterized by N, L, and M by a central frequency, which depends only on N and L, and an expansion in a polynomial where the coefficients, this is this equation I'm talking about, these coefficients are related to Clebsch-Gordan coefficients. And you can actually show that the structure, that this frequency, nu NL, depends only on the structure of the sun. The odd order coefficients, so A1, A3, etc., depend on rotation. The even order coefficients depend on the second order effects of rotation through Coriolis forces and on other asphericities such as magnetic fields. Now, normally Jmax for the current data sets is set at about 36, which is, of course, it's easier to fit 36 plus 1, 37 components than, say, 401 components for any given mode. So the error, the uncertainty on each of these quantities is very low, and I'll show you a graph later. So all the structure work is done with this nu NL, and the rotation work that I'll show is done with the odd order A coefficients. Now, the reason we can build up a picture of the sun is that different modes penetrate to different depths. Lower order modes go deeper, lower degree modes, that is low L, L of 0, L of 1, L of 2, go deeper inside the sun than high degree modes. So here in this particular figure, the red is a low degree mode and the blue is a high degree mode. And you can actually represent the oscillation equation under a few assumptions, somewhat drastic, but it's still a good indicator, as this equation here. This is a simple oscillation equation, but you can see it depends on two frequencies. SL is the Lamb frequency, which depends on L, and N is the buoyancy frequency or the Brunt-Väisälä frequency, which you recall is actually imaginary in a convection zone. So the figure that you see on the left is what's known as a propagation diagram. The dashed line shows the Lamb frequency for different L's, and the solid line is the buoyancy frequency. And if you just look at the equation, the oscillation equation, you can see that there are two regimes of oscillatory solutions. One is omega squared is greater than both the Lamb frequency and the buoyancy frequency. Those are the acoustic modes that we really observe. The G modes are ones where omega squared is less than both the Lamb frequency and the buoyancy frequency. So what happens for a given degree, a mode is oscillating. So in this case, I'm looking at this mode here, mode of this frequency. This only samples the sun from the surface to the point where the Lamb frequency for L of 20 becomes equal to the frequency of the P mode. So you can see for the same frequency, an L of 5 mode will go even deeper, an L of 1 mode would go deeper still, and L of 0 mode will actually go right to the core. This is in the asymptotic regime, but it generally works well to describe the modes. And you can, that's why, see that if we have modes of very different degrees, low degree modes, intermediate degree modes, high degree modes, we will have modes that sample different parts of the sun, so you can build up a picture of the interior of the sun. Okay, so this is just to show you what people do to observe solar frequencies. This is not my expertise, but it's in principle very simple. You take a Dopplergram of the sun. You take a Dopplergram every minute, or in the case of HMI, every 45 seconds. the biggest velocity that you see is rotation. So this is minus 2 kilometers per second plus 2 kilometers per second. That's nothing but solar rotation, well known. Remove that, what you see is supergranulation and mesogranulation. Remove that, what is left, which is the movie here, is basically what is the signature of the oscillation. So what you do is you take a spherical harmonic transform of this to get the data for different L's. You build up a time series of the different spherical harmonic transforms, and that'll then you do a Fourier transform to get the frequencies. I'm sure my friends at the HMI and Gong and MDI projects will tell you that it's not as simple as it sounds, because you have to take into account all sorts of instrumental effects, but that's the principle. And this is what the solar power spectrum, after you do the FFT, looks like. So this is degree on the x-axis. This is frequency. This is a power spectrum from MDI. And each of the ridges correspond to a different value of n. So this is the F mode, so n of 0. This is n of 1, n of 2, n of 3, and so on. And we usually use modes from as low a frequency as we can actually fit the modes to not too much higher than 4 millihertz, because the uncertainties on the frequencies become really large. So this is a sample. Here I now have points of helioseismic data that I've actually used a lot. This is 1 year of data from MDI. This is actually from its first year. So again, this is degree, this is frequency, and the reason we can do so well is this. These are 1,000 sigma error bars. The errors are tiny, the uncertainties are tiny. In fact, other than pulsar timing and a few other things, this is in astronomy, this is probably the most precise data set that you can get. And this is what helps us build up a picture of the sun. So what have we actually learned? We've learned a lot about solar structure. We've learned a lot about solar dynamics. We've actually learned a lot about the physics of solar material too, because the sun is such a well-characterized object. We can actually use the oscillations to probe properties of the solar material, like equation of states, and that's being the main one. And of course, we are constantly finding solar cycle related changes. We do not have too many solar cycles worth of data, so all we are seeing at the moment is that each cycle is quite unique. Who knows what cycle 25 is going to be like? Okay, so if I put my astrophysicist hat on, what I'd do is I'd make a model of the sun, calculate its frequencies, and compare the frequencies with that of the sun. And this is what I'm showing here, the difference in frequencies between a solar model. This happens to be the famous Model S of Christensen, Dalsgaard et al., 96. And the frequency differences, there's a bit of scatter, but it's mainly a function of frequencies. Turns out this scatter is not a physically relevant scatter, at least not this large scatter at a given frequency. This large scatter is because modes that only penetrate to the outer layers of the sun are easier to perturb than modes of the same frequency that go deep inside the sun. But we know how to correct for that. And that we correct by looking at what the inertia of the modes are. Think of it this way, F equals ma. In this case, F instead of force is the perturbing, the perturbation, m being the inertia, a being the change in frequency. So if m is large, the change is going to be small. So once we correct for it, the spread actually becomes very small, and the high dependence, there's still this huge frequency-dependent frequency difference. The spread is actually what tells us, it turns out, what the difference between the sun and this model is. This frequency-dependent huge difference comes mainly from the fact that we are pretty hopeless at modeling the outer layers of stars. For example, we use the mixing length to calculate convection. We know it doesn't work. Our 1D models do not include the dynamic effects of convection, like turbulent pressure. All of them serve to give us near-surface errors. And you can show, if you work out the mathematics of the eigenfunctions, if you make a perturbation close to the surface, the change in frequency is just a function of frequency, as long as your modes are of degree of less than about 200. So it's the surface physics causing this huge change in frequency. So this is frequency differences between two models now. The only difference between the models being we've tweaked the surface of one, that we use a slightly different atmospheric model than the other. Moral of the story is we cannot really use frequency comparisons to figure out what the sun is like, because we can't compare our models well enough with the sun. So we resort to inversions. What do I mean? We know we can cast the oscillation equations into an equation that relates directly the structure of a star to its eigenfrequencies and eigenfunctions. So this is the equation. Omega is the eigenfrequency, rho is density, c is sound speed, P is pressure, but we're talking about a star in hydrostatic equilibrium, so pressure can be related to density. G is acceleration due to gravity, which is again derived from density. So basically, the oscillations depend only on sound squared on density. The problem with this equation is we can observe omega. We want to find C and rho, but there are these eigenfunctions sitting here, and we cannot observe the eigenfunctions at all. I mean, yes, we could claim we're seeing them at the surface, but that's not quite the same thing. Fortunately for us, in Chandrasekhar, the same Chandrasekhar as the Chandrasekhar limit, showed that this actually, under a simple boundary condition, is a Hermitian eigenvalue problem. So we can use the variational principle to linearize this equation around a known model. So once we do that, what we can recast this equation as the difference in frequency between the sun and the model can be cast as an integral of, this is a known function, it's a kernel. This is the relative difference in the squared sound speed between the sun and the model. It's c squared because there's c squared in this equation, times another integral over the relative density difference, again with known kernels. And we can calculate the kernels from the solar model around which we are linearizing this problem. This is the surface error we talked about earlier, which comes from an inability to model the surface, as well as from the fact that the boundary conditions used to make this Hermitian eigenvalue problem has a very simple surface boundary condition. So this is the equation that we use. We know this, omega, delta omega by omega. We know the kernels. This is an arbitrary function of frequency, but a simple low-degree polynomial, so we can fit that out. What we need to do is find delta C over C and delta rho over rho. So a model which shows a small delta C over C and small delta rho over rho with respect to the sun is obviously a better model than models that have large sound speed differences and density differences with respect to the sun. First question, can we even do it? So, of course, we try it out on a pair of models. So, the There are two graphs here showing the inverted and exact sound speed and density differences. The line is the exact sound speed difference, and here this is the exact density difference. The points are what you get by inverting frequencies, and I've only restricted myself to the mode set that has only used those modes that have been observed in the sun. And you can see we can actually do a very good job. So in other words, we can believe our inversions. Excuse me. So this is the sound speed difference and the density difference, the squared sound speed difference actually. So if you want to know what the sound speed difference would be, you divide it by 2. These are small differences. Between two solar models and the sun, thing to note are even at the maximum difference, we are talking about fractions of a percent difference here in sound speed and a couple of percent difference in density. In astrophysical terms, that's almost a 0 difference. However, look at the error bars. These are 3 sigma error bars. That's the difference between the sun and the model. So our models may be very, very good, but there are significant differences even today between the models and the sun. The biggest difference that you see here, so that's the base of the convection zone. You see this big difference here. That is most likely, these days the consensus is, because our 1D models include the settling of helium and heavy elements, so they settle beneath the convection zone. The convection zone is, of course, chemically homogeneous, and they build up there. So since helium and heavy elements build up there, it decreases the local sound speed in the models. While in the sun, there is something going on in that region which mixes the layers so that the decrease in sound speed because of the increase in mean molecular weight isn't that high. We know, as we'll see later when we look at rotation, this is the region where the rotation rate changes rapidly. So it's likely, this is a shear layer. When you have strong shear, you have turbulence. So it's most likely that in the case of the sun, there is actually a turbulent shear layer there, which our normal 1D models are not capturing. But the takeaway point is, we do know how to model the sun. Yes, we are missing details, but we can be happy that we are not misrepresenting the sun much. And of course, since we know the difference in sound speed between the sun and a model, and we know the model exactly, this gives us what the sound speed is inside the sun. It tells us what the density is inside the sun. So in other words, we know the density and sound speed of the sun independent of whatever the sound speed and density inside a model may be. And there has been fairly extensive work to show that the inversions are indeed linear, at least with modern models. So even if you just use one model to find the solar sound speed, you'll be doing quite well. Now, because we can do inversions, we can try and determine which physical processes are important. So here, I'm again showing the sound speed and density differences between two pairs of models on the sun, except in the blue model, there's one physical process missing, and that's the gravitational settling of helium and heavy elements. Put that in. Every other physics input is the same for the two models. The moment you put diffusion in, our models become much better. And we know this is because when you're not putting in diffusion and heavy elements, you are making the convection zone of the sun much shallower because basically you have a lower opacity there. Now, so models without diffusion have shallower convection zones compared to the sun than models with diffusion. And this huge jump here is basically a mismatch in the depth of the convection zone. So this is how you can study physical processes, make different models with different physical processes, then compare against the sun. Okay, the other things we can do, not necessarily of too much importance to solar physics in general, but of extreme importance to stellar astrophysics, is what is the helium abundance of the sun? Helium abundance affects the evolution of a star. For low mass stars like the sun, the photosphere is not hot enough to actually get to see helium lines at all in their spectra. And with chromospheric and coronal lines, there's always a question of flip effects and fractionations. But the thing is, helium ionizes inside a star. In ionization zones, the equation of state effects locally decrease the sound speed. And we can, depending on how much helium you have, the sound speed will decrease because the adiabatic index, Cp over Cv, decreases. So what is shown in this graph is the relative difference in the first adiabatic index between a model with a helium abundance of 0.252 and models with differing helium abundances. So it's 0.252 minus the others. And you can see a very clear change. And basically what you do in the case of the sun, instead of finding the difference with one reference model, you find the sound speed difference with many different reference models made with different helium abundances, and you calibrate this difference to figure out at what helium abundance you get a zero difference. That's one way of doing it. The other way of doing it is to look at this quantity, which is a dimensionless sound speed gradient, which in the helium ionization zone has this peak. And I'll zoom in. That's the black peak. The colored lines are models made with different equations of state because the shape of the peak depends on the equation of state. So MHD here stands for Mihalas, Hammer, and Dayton, not magnetohydrodynamics. That's an equation of state, MHD equation of state. OPAL is a fairly well-known stellar equation of state. And you can see different helium abundances change the height of the peak. And so you can then try to find the helium which gives you the peak height. So that way we have been able to find the helium abundance of the sun. And we can also study things like the equation of state because, again, gamma 1 is an equation of state quantity. Now, at the core of the sun, you expect everything to be nicely ionized. So you expect gamma 1 to be 5/3, except because monochromatic, non-relativistic gas, gamma 1 should be ideal gas, gamma 1 should be 5/3, except you see that there is a gamma 1 difference between the models and the sun. Turns out that gamma 1 is 5/3 in the non-relativistic regime. The core of the sun is high enough that there are sufficient number of electrons that actually have very high velocities. So gamma 1 is not 5/3 but lower than 5/3 because for a relativistic ideal gas, gamma 1 should be 4/3. So in the sun, gamma 1 is slightly lower than 5/3. And these equations of state 20 years ago did not include those effects. They have since been corrected, and models made with the corrected equations of state actually show no difference. So this was one of the first instances. You can see the date, 1998, it's quite a while ago, where we actually used helioseismology to study microphysics, that is basic properties of matter. Our current headache when it comes to solar structure is the fact that there's a controversy over how much heavy element there is in the sun. You would think that spectroscopy of the sun would tell us the abundance of the most important elements properly, but there's been a controversy for the last, not quite 20 years, but 15 years, and it hasn't been sorted out. And the problem is heavy elements determine opacity. If you have low opacity, you can't really match the structure of the sun anymore. And that is basically what happens if you use different abundances to look at the sound speed difference and density difference. But I would actually like to go on to dynamics because that is much more interesting. The surprise was rotation. This is so we knew that solar surface had differential rotation, meaning it's been known from sunspot traces and other traces that the solar equator rotated faster than the poles. An application of simple fluid dynamic equations would tell you that then isorotation contours should be parallel to the rotation axis. What you see really is quite different. You see that there's a radial differential rotation. The rotation rate in the convection zone is almost similar to that of the surface. Then around the base of the convection zone, it changes. And close to the surface also, the rotation rate increases inwards. So let me show you a bit more detail. So this is latitudinal cuts. That is what's known as the tachocline, the region where the speed changes, the rotation rate changes. And that's the near surface shear layer, and we're still trying to figure out what role does the near surface shear layer play. Now, the thing about the tachocline is, in this particular inversion, it looks nice and spread out. It's not a sharp change, but that's because of the resolution of the inversions. If you do a super resolution, then you can get the change to be much steeper. Now, the fact that the tachocline almost coincides with the base of the convection zone. It's actually prolate in shape when you look at it in detail, while the base of the convection zone seems to be completely spherically symmetric. But the fact that the tachocline coincides with the base of the convection zone, unfortunately, means some people conflate the two. Tachocline is a change in dynamics. The base of the convection zone is a change in structure. So one has to keep that distinction in mind. And tachocline is, of course, where we believe the primary solar dynamo resides. Okay, the other types of stuff that we can see from our from helioseismology, not from the same modes that I showed you, but nonetheless with helioseismology, is that there are flows from the equator to the poles in both hemispheres. These results are only confined to the outer 15 to 20 megameters, unfortunately. People are trying desperately hard to see where the meridional flows close. This is another way of doing it where these two groups have done a deeper inversion, but you can see that the features don't always match.
5 minutes to go.
Mm-hmm. And the reason people are interested in this is the flux transport dynamo theories. Most of them rely on a return flow of the meridional flow happening close to the tachocline. And we don't quite see the return flow yet. About solar activity related changes, I'm going to skip the movie, but go to the next page. Not quite the next page. This shows the change in frequency. So solar frequencies change with solar cycle. And that most of the changes are actually pretty well correlated with changes in activity indicators. So in this case, you can see it's basically the black line is the SF10 and is the RF10 flux. And on that, I've plotted the frequency changes, and they follow almost exactly. They didn't follow this well for cycle 24, actually. This is for cycle 23. And there are some changes in structure, but the changes in dynamics are most interesting, particularly if I take the average solar rotation rate and subtract it from the solar rotation rate at each point, you get these residuals, which you see in this movie, but this is not a very interesting way of showing them. A better way of showing them is to plot them as a function of time and latitude at different depths. And then you can see these patterns of prograde and prograde flows going from solar minimum to maximum going towards the equator, and then there is this high latitude branch of the flow going towards the poles. This is an older result. Rachel Howe has a more recent result, which shows that maybe cycle 25 is beginning. That's cycle 23, cycle 24, perhaps cycle 25. And you can see that the poleward flow was actually pretty weak out here. It's just about. So there are changes, there are differences in dynamics of the two hemispheres that go more than just what we're seeing on the surface in terms of sunspot numbers and radial fluxes. Meridional flows too change. They are slower during solar maximum than during solar minimum. So that's solar minimum, solar minimum, solar maximum. These are at two different depths. And the thing is, we can subtract the average zonal flow, and what we are left with are long-lived patterns at high latitudes. You see these. These are, the gap in the middle is because even with HMI, we have too much foreshortening above a latitude of 75 to 80 degrees. Depending on the B angle of the sun, sometimes we can go higher in latitude. So that's the pole in the middle. That's our zone of exclusion. We can't see anything. That's the equator out here. And you see these long-lived structures. They can live for a month or two. We can't, of course, say what's going on in the pole. Now, we can speculate. My bet is on it might end up looking like Jupiter's poles, now that we know there are multiple whirlpools very close to the poles of Jupiter. So we really need a mission to figure out what's going on here. And, okay, I'm going to close not with conclusions, but just a list of questions which we haven't yet been able to answer. Where do the meridional flows close? That's important for our dynamo theories. What happens at the poles? Why do we care? Because again, flux transport dynamo models say that the flux is transported to the poles where they go inside with the meridional flow and then reappear at the equator. Then zonal flows and sunspot butterfly diagrams actually have a nice relation. So what's shown here, black points are the butterfly diagram, and the colors are the gradients, the radial and the latitudinal, upper part radial, lower part latitudinal gradient of this east-west zonal flow. And the maximum gradients correspond to where we see the butterfly diagram. So which came first? Which is the chicken and the egg, and how are they coupled? Because they must be coupled fairly non-linearly, I would imagine. And what is that? So I've shown you some of the results that we found with the sun. The results about structure are actually explained quite easily with basic physics. Dynamics, on the other hand, is still causing problems. So thank you for your attention.
Okay, so thank you very much for your talk. Now we are open for comments and questions. Martin, yeah, go ahead.
A question. Thank you, Siobhan. It's a nice talk. So this is Martin from NRL. I have an ongoing argument with some of my colleagues in the solar wind community who think that gravitational settling can occur throughout the convection zone.
Oh, they do occur throughout the convection zone. But the problem, of course, is that we are not going to see the see a radial gradient because of gravitational settling in the convection zone, because the mixing time scale is much shorter than the settling time scale. So what happens as a result is that all we are seeing through evolution is that the total amount of helium and heavy elements in the convection zone becomes lower than what it was born with.
Okay, okay.
And
I always assumed that this would be much smaller in the convection zone than the radiation zone, because if you think of nature convection, you take
yes,
it from the bottom of the zone and put it at the top. You know, the constant turnaround should inhibit.
Well, the thing with the convection zone, of course, it's easier to see because we're talking about stars which have an outer convection zone.
Yeah.
What's happening in the radiation zone is, of course, what's coming out of the equations, which may or may not be correct. And as we said, in the case of the sun, we are missing a main factor, which is extra mixing below the convection zone. But the diffusion, of course, is also a function of temperature, and so if you have a very thin convection zone, and this is something we find from work in stellar astrophysics, current diffusion coefficients seem to be completely incorrect because you try to model a 1.3 solar mass star, very soon it'll get completely depleted of all elements, of all heavy elements, and we know that can't be correct.
Yeah.
But in the case of the sun and stars roughly the same mass as the sun, this seems to work very well.
Okay, so the thicker convection zone, you can have diffusion.
Yes, you can have diffusion.
In the convection zone, you end up with problems. Yeah.
And we see that in the sun. We know that the current helium abundance of the sun, thanks to helioseismology, we know it's about 0.25. But to explain the luminosity of the sun must have been born with an initial helium abundance of 0.27.
Okay.
And so that is exactly how much settling that you see. So even if you make a solar model without settling, the initial helium abundance you need is 0.27.
Okay, yeah.
Even if you make one with settling, you'll still need 0.27. So that explains the current luminosity. But it doesn't explain the current surface helium abundance.
Okay, and the other thing I wanted to ask, you glossed over very quickly, you said it wasn't interesting. Something is the atomicity of the sun, specifically
it's very interesting depending on what your point of view is. So, can you see this figure?
I put my glasses on.
So,
okay.
So GS98 is a model with the old Graves and Sauval 98.
Yes.
These are the higher abundances. AGS09 are the lower abundances by Aspland, Graves, Sauval, and Clark, which incidentally is still much higher than the original low estimate. So this is what it is. So
yeah. Okay.
So they actually have increased their Zeola X.
Yes. So, but you're favoring the higher oxygen abundance of Kappa.
Yes. And with Kafau et al., even though the total Z is different, the distribution of elements is such that the opacities sort of balance each other out, and you get a model which is not too different from the GS98.
Interesting. We have a paper on analysis of the Genesis return samples, and that's favoring Kafau over Aspland and co-workers.
I would think so. I mean,
it's a preliminary analysis, but that's looking for FIP and all these other things, and that's coming down in favor of Kafau.
Oh, that's good. Yeah. Okay.
But you should take that with a probably very, very small grain of salt.
That's okay. So I'm also waiting to see the people are beginning to measure neutrino fluxes from CNO reactions. And those will actually be a completely independent test of the metallicities.
Yeah.
So, because lower metallicity means slightly lower CNO rates.
Okay, I'll let someone else ask a question now.
Okay, other questions or comments? Okay, everyone is muted. I have a minor question. Looks like the magnetic field is not part of the picture. Does it play any role at all or not?
It probably plays a very large role very close to the surface. So I had mentioned earlier that the odd order coefficients, let me go back to the slide. The odd order A coefficients is rotation, and the even order A coefficients is second order effects of rotation, and everything else. And the everything else includes magnetic fields. If I assume that the everything else is only magnetic fields, then I can use the even order coefficients to try and figure out what magnetic fields are. And what we find is that when you do that, all you can say is give statements about magnetic fields in the outer, say, above 0.96 solar radii. What happens deeper inside is that to all intents and purposes, I mean, given that the even order A coefficients are so low, you don't even have to do anything to actually show that it means that the magnetic pressure is much smaller than gas pressure. And you're not going to see a change in the frequencies, which will tell us anything about magnetic fields, unless the magnetic pressure is reasonably similar to the gas pressure. So there are upper limits to the magnetic field at the base of the convection zone, and those are sort of less than 0.3 megagauss. Once upon a time, apparently, that was a big problem for dynamo models, but I'm told no more, that's not a problem for dynamo models anymore. So the interior of the sun, magnetic fields don't appear to play much of a role. Of course, in the very outer layers they do, but any change in the outer layers just appears as this, as this frequency-dependent frequency error. In fact, if you look at, let me go to the solar cycle change picture, the movie that I did not show. Look at the frequency differences between solar minimum and different epochs. It's again just a function of frequency, once you take the mode inertia into account. So yes, magnetic fields are changing things, but the role seems to be confined to the outer layers, the visible layers. This would be quite different from some very low mass stars that my planet search colleagues are interested in. They like M dwarfs, and M dwarfs are horribly magnetic. And we should be glad we don't live around an M dwarf.
Okay, thank you. Last call, any last questions? Okay, everyone is muted, so let me thank you again for this very interesting and instructive talk. So, and next one will be in 2 weeks about three-dimensional modeling in the chromospheric and coronal by GeoLunita, so I invite everyone. So thank you very much.
Thank you very much. Thanks.